All right, welcome back everybody. In this video, we are going to start working on Unit 1, Section 8 of AP Calculus, determining limits using the Squeeze Theorem. This is probably the first of what will likely be 2 videos, maybe 3. We'll see how things work out. So we're going to start right off the bat by introducing what's known as the Squeeze Theorem. And for older people like me, I know this used to be referred to a lot as the sandwich theorem when I was younger. So you might see it referred to as the sandwich theorem some places, but we're going to call it the Squeeze Theorem, and the College Board refers to it as the Squeeze Theorem as well. All right, so you see it boxed in here. Suppose that f of x is less than or equal to g of x is less than or equal to h of x for all x in an open interval containing a, except possibly at a itself. If the limit as x approaches a of f of x is equal to the limit as x approaches a of h of x is equal to L, then the limit as x approaches a of g of x is equal to L. And let's take a look at what this looks like graphically. First of all, we've got this function h of x. There's my generic h of x. And we've got this other function g of x. Well, let's do f of x next. We've got this other function f of x. And the way this is written here is that f of x is less than or equal to g of x is less than or equal to h of x, but that the limit as x approaches a of f of x and h of x are both equal to L. So I'm actually going to bring this up just a little bit here so that they equal the same value. And I'm going to call this value right here a. And then what this means is, since g of x is always between f of x and h of x on the open interval containing a, that means that g of x always has to be in between the blue and the purple graphs here. And since the top graph and the bottom graph both have the same limit as x approaches a, that means that the graph that's sandwiched in between them, or squeezed in between them, also has to have that as its limit. And that's our Squeeze Theorem right there in a nutshell. Okay, let's move on to our first example. Is being bounded enough? The function f of x equals sine of 1 over x is bounded from below by g of x equals negative square root of 1.2 minus x squared, and from above by h of x equals square root of 1.2 minus x squared on the interval from negative 0.5 to 0.5. Is there enough information to determine the limit as x approaches 0 of the sine of 1 over x? Okay, so in order for us to be able to determine the limit as x approaches 0 of the sine of 1 over x using the Squeeze Theorem, what we would need is, we have g of x, which probably is above sine of 1 over x. Well, it says bounded from below by this, so it is. And it's bounded from above by this. So basically, if those two limits, the limit as x approaches 0 of g of x and the limit as x approaches 0 of h of x are the same, then we can determine the limit as x approaches 0 of sine of 1 over x using the Squeeze Theorem. So I'm going to go ahead and find these limits. Limit as x approaches 0 of g of x is which is approximately the opposite of the square root of 1.2. Or negative 1.095 approximately. And the limit as x approaches 0 of h of x is approximately positive 1.095. So, do we have enough information to determine the limit as x approaches 0 of the sine of 1 over x? We can't. determine limit as x goes to 0 of sine of 1 over x using the squeeze theorem I did a Billy Madison Z there. Squeeze theorem because limit as x approaches 0 of g of x does not equal the limit as x approaches 0 of h of x. So the squeeze theorem is no help for us there. All right. On to our next page, and our next example. Example 2. Suppose there are three functions such that f of x is less than or equal to g of x is less than or equal to h of x when x is near 2. Okay, good. If f of x is equal to this first function and h of x is equal to this second function, then find the limit as x approaches 2 of g of x. And so knowing this relationship, this example is kind of setting us up to use the squeeze theorem to find the limit as x approaches 2 of g of x. So in order for us to find that, what we first need to do is find the limit of these other two functions. So I'm going to find the limit as x approaches 2 of f of x, which we're going to get by just substituting 2 in there. And that gives us, let's see, -1 if we calculate all that out. -8/3, -7/3 makes -5, and 2 squared is 4, so that gives us -1 as our limit. And the limit as x approaches 2 of h of x is equal to the cosine of pi over 2 times 2, so cosine of pi, which is -1. Since we know that g of x is in between f of x and h of x, and we know that the limit as x approaches 2 of f of x equals the limit as x approaches 2 of h of x, that tells us that the limit as x approaches 2 of g of x is equal to -1. Because of the squeeze theorem. You know, since this and both of those, then the limit as x approaches 2 of g of x is equal to -1. All right, let's go ahead and we'll look at example 3 here. It says, let f, g, and h be the functions f of x equals x squared sine of x, g of x equals e to the x sine of x, and h of x equals e to the x over sine of x, for x not equal to 0. All of the following inequalities are true on the interval from -1 to 1 for x not equal to 0. Which of these inequalities can be used with the squeeze theorem to find the limit of the function as x approaches 0? So first we start with statement number 1. -x squared is less than or equal to f of x. So we're focusing on our function f of x here. So -x squared is less than or equal to f of x, which is less than or equal to x squared. We're told that all of these inequalities are true. If we take the limit as x goes to 0 of -x squared, we get 0. If we take the limit as x goes to positive x squared, as x goes to 0, both of those are 0. And therefore, the limit as x approaches 0 of f of x, we know has to be equal to 0. So this inequality can be used with the squeeze theorem to find the limit of the function f of x. All right, next let's focus on g of x, e to the x over sine of x. And this one looks like it might be a little bit tougher maybe. Okay, so let's see. The inequality is true. So g of x is in between those two. Now, in order to figure this out, we need the limit as x approaches 0 of these two functions to be equal. Well, the limit as x approaches 0 of these two functions, well, this limit right here, that doesn't even exist. Neither does this one. And therefore, they're not a finite value that g of x can be squeezed in between, so this statement is false. It can't be used to find the limit as x approaches 0 of g of x. And part 3 here, we're using the function h of x. We're talking about, all right, so h of x is in between those two. And we sandwich them. If we take the limit as x approaches 0 of this function, it's equal to e. And if we take the limit as x approaches 0 of this function, it's also equal to e, which means that those two limits are equal. And since h of x is in between those two functions, its limit must also be e. So this one also works to help us find the limit of h of x. And so our answer here is going to be choice 1 and 3. All right. I'm going to show you that really quickly. Use my graphing calculator here. I'm going to use Desmos to show us what's going on there in this last one. We've got 1/4 x squared plus e as one graph. We've got x squared plus e as our second graph. And then sandwiched in between them is e to the x over sine of x. And we'll zoom in here a little bit. Come on. Zoom in here a little bit around 0, and you see that the green graph is in between the red graph and the blue graph, close to 0. And that all three of them approach this same value as x approaches 0. Let's compare that to what happens in example B here. If we graph 1 over x, and we graph, what's the other one? X plus 1 over x squared. We graph those, and we try to use that to help us find the limit of e to the x over e to the x over sine of x. And what you can see here is you can see as x approaches 0 that all these graphs, you know, the red graph is in between the purple graph and the black graph, but it never gets sandwiched because the purple graph and the black graph both go to infinity and they never really squeeze together. All right, so that's it for today's video. You can go ahead and close me down, and I'll see you next time for video number 2 on Unit 1, Section 7, determining limits using the Squeeze Theorem, or pardon me, Unit 1, Section 8. All right, have a great rest of your day, everybody. See you next time.